So sometimes we want to look at how two propositions are related. And so if we have a proposition, which could even be compound, if we have a proposition P, we might want to know if its truth implies the truth of something else. And so we refer to these as implication, and we represent that as P long double arrow Q. And we say P implies Q. And this is true when the truth of P implies the truth of Q. If P is true, Q is true. What we're not saying is anything about what happens when P is false. So P implies Q is true unless P is true and Q is false. This is the only time that this implication doesn't hold. We're not saying anything about what happens when P is false. So if we look at that truth table, the only thing that we're actually worried about is that second row. So when P is true and Q is false, that means that implication doesn't hold, because we want to know that when P is true, that implies that Q is also true. So this is the one time that P implies Q as a compound proposition is false. It might seem odd that we have this situation here where false, true as a combination also is true. But that's because we don't know what happens when P is false. Because P was false, it's true. It does not go against that in the slightest. When we talk about P implies Q, there's a couple words that can be used to represent those propositions. The first is that P is the hypothesis. In mathematical terms, sometimes we refer to this as the antecedent. Q is often referred to as the conclusion. It's also sometimes referred to in mathematics as the consequent. It's what happens as a consequence of P being true. In the English language, an example of a proposition of this form might be something as follows. If it is raining, there is a rainbow. So note that it says, if it is raining, there is a rainbow. Both of these are facts that we can check. Where it is raining is our atomic proposition P. There is a rainbow. That's our proposition Q. And really this is saying it is raining implies there is a rainbow. What is not an example of a compound proposition P implies Q is something of the form, if it is raining, look for a rainbow. That's a command. But these are facts that we can check. We can check if it is raining is true or false. We can also check if there's a rainbow. There either is a rainbow or there is not a rainbow, but there's no way that it can be somewhere in the middle. And so this is an example of implication. Note that what this sentence doesn't say is anything about what happens if it is not raining. Could there be a rainbow when it's not raining? Probably not. But it's not implied within this sentence. And so if there happens to be a rainbow but it's not raining, the sentence is still true. The only way this sentence becomes false is if it is raining and yet there is no rainbow. The next way that we want to look at how we can combine atomic propositions is the proposition P exclusive or Q. And this is sometimes referred to as XOR, and it's always represented as such. So it's a plus with that circle around it. And this is true when one of P and Q is true, but not both. It's only one of them can be true. So it is false when the truth values of P and Q are both true or both false. If we look at the table, what that means is only those second and third rows where exactly one of those has a truth value of true, are we going to end up with true, with a truth value of true for P exclusive or Q. In the rest of those situations, the truth value of P XOR Q is false. So what does that look like in English language, and why would we need this special connective? And so if I say, on Tuesday, I will either be in China or Toronto, what we see is that not both are meant to be true. So on Tuesday, I will either be in China or Toronto. Well, being in China, we can take as our P, Toronto as our Q, and we're not suggesting that both will be true. And so this compound proposition is going to be true if I'm in China or if I'm in Toronto. But I can't be in both places on the same day. And so while it's false if I'm in neither China or Toronto, it's also not going to happen that I'm in both. And so this is a great representation of P exclusive or Q. And finally, we want to look at this connective if and only if. The proposition P if and only if Q, represented by that double long arrow that goes in both directions. So it goes from P to Q and from Q to P. And this is true when P and Q have the same truth value. And you can kind of think of it as P implies Q and Q implies P. It's going in both directions. So it's true when they have exactly the same truth value. And what that means is when we look through this, we see that on the first line, P and Q are both true. On the last line, P and Q are both false. And so these are the only times that is true. In the other situations, they don't map to each other, right? P is true and Q is false, or P is false and Q is true. So the only time that P implies Q is true is when both P and Q have the same truth values. They're false in the other situations. Let's take a look at sort of the trickiness of what this can look like in the English language, because we don't often use the phrase if and only if, but sometimes we imply it. And so, for instance, when we give definitions such as a number x is even if x mod 2 is equal to 0. So what we have is two atomic propositions. A number x is even, and Q, a number x mod 2 is equal to 0. And then we see they're connected with just this word if. But what we're actually saying is x is even implies that x mod 2 is equal to 0. But we're also saying that if x mod 2 is equal to 0, then x is even. And so it's not always clear if what we're saying is if and only if, or if, when we use that word if in language. These conditional statements are going to come in many forms. So even when we look at implication, it's going to come in many different facets. So implication and this concept of if and only if, that biconditional statement, comes up in many different ways. So in English language, we'll hear things like if P, then Q, if P, Q, Q if P, Q when P, P only if Q, Q whenever P, all of these things, Q provided that P. There are going to be many different ways that you might see that in the English language. And an example that we might consider is, if I'm elected, then I will lower taxes. In order to understand that sentence, if I'm elected, then I will lower taxes, it's useful to think of the obligations at stake. So if I'm elected, then I will lower taxes. If the politician is elected, voters are going to expect that politician to lower taxes. So if the politician is elected is true, then we hope that that would imply that lowering taxes is also true. But if the politician is not elected, then there's no expectation made that that person will ever lower taxes. So although the person might have the influence in order to do so, they're not required to in terms of what that sentence would have implied. And that, in a nutshell, is our introduction to logic. We'll come back later and we'll take a deeper dive into other aspects of what we can do.
I really like logic.
I do too.
But I'm not satisfied with what we've covered so far. Can we do more? I really like puzzles.
I definitely want to make sure that you're satisfied with what we're covered. So next time we'll cover satisfiability. And this is an exploration into whether or not a specific logical statement can be satisfied if there's some combination of truth values for its atomic parts that will allow it to become true. We'll also take a look at some puzzles.
Thanks for watching.
See you next time.